we're on time to begin our session today. Welcome, colleagues, to the second day of the HLS Solution 2022 conferences. I am Arnaldo Saavedra. I work for Freeport McMoran Copper and Gold, and in the Phoenix office. I work for the PCLW group as a Chief Geotechnical Engineer. Today, we are going to develop the session 6, which cover the following topics: engineering design, geotechnical track, and new technologies. We have 6 sections scheduled, 4 in person and 2 virtual. The first presentation is titled on the use of buried pipes in heap leach facilities. The expositor is Bryan Ulrich. Bryan is the owner of Bryan Ulrich LLC. Bryan is a recognized leader in the geotechnical design in the mining industry. He's a geotechnical engineer with more than 3 decades of experience with engineering, project management, design and construction, analysis, and site investigation of mining-related work. Please join me. Welcome me, Bryan.
I'm going to talk to you about drainage pipes and heap leach facilities. And it's not everything you ever wanted to know about drainage pipes, but it's just some thoughts that I had to put together. So, as you said, I'm Bryan Ulrich at my own consulting firm these days. Also have a podcast and a blog and some. So I wanted to have a little safety share first. And this is a vehicle that I saw exiting the parking lot. I just kind of got a kick out of it. It says safety third. Obviously, nobody puts safety third. He must have been a safety professional. Safety is always first, right? It may not be first by itself, but there's definitely first. So we've got a change of seasons coming up here in North America. Snow's going to be flying. It's going to be icy roads and stuff like that. And just be aware, especially the first time you go out on snowy roads. This is a picture of my Jeep, just showing you that sometimes people in Jeeps don't do what you think they would do. But anyway, driver safety, changing conditions, winter driving. But just be aware of that as winter comes on us. So I wanted to share with you one of the reviewer comments that I received early on. I said, this paper deals with a very important topic. And so that gave me the confidence to keep on there. There is a lot of previous work on this. A guy named John Nuku presented a paper at the SME annual conference in 2001, a really good paper. And you should leave now and read that paper. And where are you still here? Okay, so this is the components of a heap leach facility and drainage system. On the top, we've got the drains. On the bottom is the liner, and right above the liner is the pipes, of course. Here's what the pipes might look like. These are pictures of a heap leach facility in Nevada. Some big pipes and some little pipes. And I'm not sure if I agree with this installation here where these pipes are above the support and they'll have to be filled with overliner underneath there. Maybe not the best application. I'm not promoting this application. I'm just showing you some example photographs. So if you did design it this way, you'd have to figure out how to support that without those pipes becoming disconnected. And they're still going to have hydraulic capability, but there may be holes exposed in these pipes if that pipe breaks away from it. So there's also the consideration of drawdown of fluid. There's a lot of different equations and approaches to calculating the drawdown, pipe spacing, the permanent loading, all that. This equation here, I'm not sure if it would blow up in use in deep because we have to subtract that height, and I think if you have a 500-foot high heat, there might be problems with that equation, but there's a lot of equations but the local agricultural drainage regulations, able to publish papers on it. But anyway, there's a lot of ways you can calculate the average and minimum heads between pipes and get your pipe spacings. But this paper really isn't about that. It's more about the survivability of buried pipes. But that is also an important topic. So let's talk about burial depth. Here's some manufacturer guidance. On the right-hand side is a dual wall pipe, smooth interior, corrugated exterior. And that's what I'm really talking about, in addition to the uncorrugated solid HDPE pipe. So this first chart here is from ADS, and it's their recommendations for pipe burials. And for this single wall pipe, corrugated only, they recommend a maximum burial depth of 8 feet. So these pipes really shouldn't be used in heap leach facilities, or you'd have to be very careful in selecting them anyway. So here's more information from ADS. This is the dual wall pipes, the Nicol dual wall pipes, and they've got 2 different categories, different classes of fill, but they've got pipe diameters for compacted and dumped backfill. So the deepest they recommend for compacted backfill around the pipe is 44 feet, and that's for a 5-inch diameter pipe. And most of our heaps don't have fill backfilled around the pipe, so the deepest they recommend there is 20 feet. And most of our heaps are quite a bit deeper than that. So the recommendation from the manufacturers is much more shallow than we normally use. So there's some pretty interesting information available in the literature. This is Pennsylvania had an experiment they call the PennDOT burial study. They buried pipes up to 100 feet in depth, so it's a little better than the 8 and 20 and 40 feet that we were looking at. And they indicate that despite those tremendous soil loads, the total pipe deflection was pretty small, 4.3%. So that sounds pretty reasonable. But again, those are the depths somewhere around 100 feet, so not really all that much for a heap leach facility. Here's some funny illustrations that I found from the New York State Department of Transportation. So here's some thin fill over a pipe. One of the things I get a kick out of is the faces that they put in here. So here's some thin fill, and here's some thicker fill. And I'm not really sure what those expressions are showing, but here's some even thicker fill. And that guy's looking pretty grumpy, and here's some really thick fill. And I thought the first one looked like a smiling sunshine face, with a little sunshine around him. But our pipes must be really frowning face, because they're a whole bunch deeper than the frowning face down on the lower right-hand side. Some additional illustrations from New York State DOT. If they've got good site support, they're also a smiley face, but if they don't have that good site support, a frowning face. So our pipes almost never have good site support, right? Places fill around them normally. Here's some more guidance: is to tamp the backfill firmly around the underneath side of the pipe. Make sure there's no void, but we almost never tamp the fill around our pipes. So how come our pipes work so well in each facility, or in March? And here's Captain Obvious saying, "Hey, my pipe looks, they're a lot deeper than the manufacturer would recommend. What gives?" And he's right. So the bottom line is, we don't install pipes like other industries. We don't install pipes like the manufacturers recommend. So here's a little comparison between civil applications and mining applications and trading pipes. So in the civil application, you install the pipe and will form trench. In a heap leach facility, they're almost always in an open surface. In a civil application, they say to leave the 1/3 of the metal bedding should be placed loosely. Ours are compacted uniformly in the bedding. Compact and fill into the haunch in prescribed layers. All we do is to ensure that the haunch is filled with overlayer or whatever material that is. Civil application, the remainder of the pipe should be placed in compacted layers. We don't compact our material back. And they say compacted effort depends on the soil type. Again, we don't compact. So much different application. Theirs is very controlled. Ours is not controlled in the same way. So how come ours work? Well, there's an experiment called the Ohio experiment, which was pretty cool. They had HDPE and PVC pipes, not very deeply, 20 and 40 feet deep, but it's still some pretty interesting information. They had soil pressure cells that were installed above the pipes at various depths, and including one that was installed only 1 inch above the pipes. And that's what we're really interested in. The test showed that the vertical earth pressure was normal, except very near the pipe. And so we want to look at what's going on there. So the earth pressure was very much reduced close to the pipe. So how come? Well, there's a guy named Carl Terzaghi. There he is, looking very impressive, the father of soil mechanics. And in my mind, he was sitting at McDonald's one day having a Big Mac and fries. And he was suddenly inspired, got an idea because he looked outside the window and saw the gold arches. And so he came up with his theory of arches. I don't know if that's a true story. So Terzaghi explained this in an analogy. In the analogy, there's a layer of sand above the solid base. In the center of the solid base is a trap door. Terzaghi actually refers to it as a strip rather than a trap door. If the trap door is open slightly and slowly, the sand in the immediate vicinity of the trap door will subside into the newly created void. And friction within the remaining sand mass resists full movement of the sand into the void. The reduction of stress on the trap door is balanced by the increase in stresses elsewhere in solid pipe. And in the case of a deeply buried pipe, if the crown of the pipe yields slightly, that is, it acts like the trap door, the stresses of the overlying soil are shed to the surrounding materials, and the vertical stress on the pipe decreases towards zero. That's why in the Ohio experiment, that pressure cell just above the pipe shows very reduced stress, because the crown of that pipe had indented and was exhibiting arching. This is what's saving our bacon in these deeply buried pipes is arching. We know that this is true because we see that in instrumented pipes and in finite element analysis. So we know that occurs. So one of the key takeaways: the pipes installed in complete facilities are typically buried much deeper than advised by the manufacturers, much deeper than most civil non-mining applications. So probably the most important factor in constructing those pipes in bleach facilities is to make sure the material surrounding the pipes is dry, granular, and flows freely under the haunch of the pipes. This provides support to the lower half of the pipe and allows soil arching to take place. And one of the really important things to consider is that fill needs to be dry. So if you're ever placing these in wet conditions or that fill is wet, so rain or storm, stop placing those because it's not going to pull the haunch of the pipe. So I had a QA engineer one time when I was explaining this to him how important it was to get that fill in the haunch of the pipe, and he was not even simple. I said, "You know what the haunch of the pipe is?" And he got it quiet. So don't assume that people know what you're talking about if you mention the hunch of a pipe. So here's a picture of a pipe, and the hunch is just the lower half. So like in that previous figure here, the lower half of the pipe is really important to that pipes surviving the burial and being able to carry out its job as it's supposed to. So just make sure that bill comes in the lunch. One other piece of advice is maybe instead of having everything up on top of line, maybe we could entrench some of the pipes in the facility. Not all of them, but the larger diameter pipes, small pipes, not so much, but those large diameter pipes. Let's put some of those in trenches so they can have the site support like we saw in some of the earlier slides. We don't want them all to be front faces. And one other thing to think about is to do camera inspections on some of those big pipes once in a while to see how well they're doing. That brings us to the end.
What's that? Let's try to stand out there.
Thank you.
The title of the next presentation is Criteria to Estimate and Use Peak and Residual Shear Strength of Interface in the Heap Pads Design. Expositor is Waldo Huallanca, Operation Manager from Andes, Peru. Waldo Huallanca is a senior geotechnical engineer in Andes based in Peru. He has 13 years of experience in geotechnical design for mining projects. He has programmed and developed geotechnical investigations for earth dams, mine roads, tailings dams, heap leach pads, and waste dams. Please join me in welcoming Waldo.
Good morning, everybody. Thank you, Arnaldo, for those introductions. I'm excited to be talking about our research. In the area display, we have received a shear strength of interface and each part design. As you know, one of the most prominent mining structures is a each part. Where the pregnant lead solution pass through the ore and is collected by the connection in the liner system in the bottom of the pads. The characteristics of the liner system depend on the environmental regulation, risk associated with the solution leak, relation characteristic, operating equipments, high heat, and slope stability. The liner is usually composed by a clay soil called a clay liner. And in some cases, even placed for a geotechnical for a GCL. And then we have a liner, a human bed, and then a liner that is protective materials. So, and one of the main restrictions of geotechnical design of heap leach pad is related to the strength of the liner system, which usually provides at least two interfaces or a liner with human brain and human brain with soil liner, both with low shear strengths due to the contact with the human brain. This interface also can control the stability of the link. The shear strength of interface is measured by a large scale VHR. You can see in this picture, following the ACM. This picture shows the typical behavior of the shear strength versus displacements. The shear stress of the generally increase until the peak shear stress. It should be noted that beyond the maximum displacements of the test, there's no additional reduction of the shear strength, indicated that in this specific case, as many others observed testing results, especially in large scale shear test for mining applications, the post-peak shear strength is very similar as a shear strength. In the first part of our investigation, we propose empirical formulas to estimate the shear strength of geomembrane with soil liner and overliner with geomembrane. So, in this research, we have complied 64 large-scale direct shear tests on overliner with smooth geomembrane, and 388 tests on soil liner with simple site express geomembrane. The comparative tests were carried out with a specific material for different mining projects collected during the last 10 years, mainly with a liner low density geomembranes for different normal stresses. You can see we have a restriction. The maximum normal shear was 800 kilopascals. The test data were divided in 5 groups based on the interface type, soil classification, the fine contents, and the characteristic of the soil and the geomembranes. Each group are summarized here in the table. You can see the kind of interface and the main properties of the soils for overliner and soil liners. The next slide shows the shear strength relationship for the overliner with smooth geomembranes interface. A relationship of each normal stress was defined based on the influence of the gravel contents. Most of the data were obtained from the test interface with LLDT geomembranes. The thickness of the geomembrane has not been considered. Also, the overliner correspond to subangular and subrounded gravels. The maximum particular size of overliner was 3 inches, and the maximum normal stress was 800 kilopascal for the test. In the figure 5, show the proposed relationship between gravel and post-peak shear strength. In the picture 6, show the relationship between the gravel content and peak shear strength. In picture 7 and 8 show the same relationship, but with a lower and upper boundaries that is based on one standard deviations. As you know, there's a clear nonlinear tendency for shear strength to increase for post-peak and peak value. The standard deviation for peak shear strength and for post-peak shear strength is lower when we increase the normal stress. In the table, we can show the formulation to determine the stress shear strength for different normal stress based on the gravel content and the energy you can replace, and you can obtain a nonlinear envelope to use in a preliminary slope stability. So, for the interface with geometry and soil liner, we can do the same, but the empirical formula, and in this case for texture geometry with soil liner, was obtained by the influence of the height or of the specific height of the geometry in the kind of soil. The result and the previous result or the combination of results could be used to run a preliminary slope stability analysis of vintage path for block failure. Regarding the data of these correlations, most of them were obtained from shear tests between soil liner and LLDT simple site express geomembranes. But as mentioned, the thickness of the geomembrane has not been considered. The maximum normal stress was 800 kilopascals. And in this case, we didn't consider silty soils because we don't have enough information. And the lab correlation was low. In this group of plots, we can present the relationship of different kind of soils. In letter A, this is for clay gravels, letter B for clay sands, and letter C for clays with fine contents below 265, and letter D with for clay soils with fine contents up to 65%. The proposed empirical formulas for post-peak shear strain are summarized here, based on, as I said, in a specific height, and consider different normal stress and different kind of soils. With this formula, you can obtain a nonlinear shear strength resistance for different kind of soil and different normal stresses. And what about peak shear strength for soil liner with geomembranes? Well, the empirical relationship were not defined due to a low correlation coefficient and a high standard deviation. For the reason we don't show formulas for peak values to this kind of interface. What happened with this information in the slope stability analysis? The limit equilibrium method is commonly used to evaluate the stability of the heap leach path. In this method, the interface is modeled as a continuous element like a soil layer. The analysis criterion that is most widespread and accepted in the practice usually assume that the mobilized shear strength can reach or exceed a peak shear strength for the materials. Thus, post-peak shear strength is usually considered in stability analysis. However, this criterion can be very conservative to estimate the factor of safety in a specific situation as a static condition, for example. The influence of the shear strength was studied by another authors such as Gilbert here, who indicate that the peak shear strength mobilized between 1 to 15 millimeters, and the displacements in large scale shear tests. I'm sorry, the author mentioned that the post-peak shear strength can be low as 30% lower than the peak shear strength. So, what about the current investigation? We found that the overliner with geometric shear strength is mobilized between 12 to 22 of the shear displacement. And the geomembrane soil liner peak shear strength is mobilized between 7 to 32 millimeters. And the post-peak shear strength for both interface can be as low as 14% of the peak values. So, as this information is logical to use the post-peak shear strength for the interface in the liner system design due to the progressive failure across the liner, more like the shear stress. The suggestion of different authors that use the peak post-peak shear strength in the design are summarized here, listed from the most to the less conservative. Starting to prepare, suggests the use of the residual shear strength for all conditions in the steps and in the flat of the leach path. Then Corner and Bowman suggests the use of the post-peak shear strength of the interface in the, with the lowest peak shear strength of the 2 or 3 interfaces that we have. John suggests the use of the peak shear strength at the base of the slope and the post-peak shear strength along to the steeper side. Corner and Bowman again.
Do you want to do mid post?
Suggests the use of the peak strength at the top of the slope and the post-peak strength.
I can do it. I don't know if you want to do
it. Again, Corner suggests the use of the peak strength for all static conditions in the base and in the single zone. Well, in our research, we evaluate the use of the peak shear strength for flat zones and the post-peak shear strength of the single strength for the single zones of each pads. And the findings compare with the numerical analysis. Therefore, three case studies were performed using field element method and limited equilibrium method. One of the cases considered 5 meters, which is presented in the interface shear strength parameters were obtained from the large scale shear test conducted for both interface. The envelope of this result you can see in these blocks in color red for the soil liner with a geomembrane. This is for the post peak and this is for peak values. In color blue for the overliner with the geomembrane. So the mobilization of the shear strength along interface below and above the geomembrane has been evaluated by numerical analysis to estimate the relative shear strength in each interface. The relative shear stress indicates the proximity of the mobilized shear stress to the shear strength of the failure envelope or the maximal shear strength. With this expression, you can understand the relative shear strength. When we are near to when we are close to 1, it's possible that the shear strength is near to the peak value, and it's possible to exceed this value, and we can use post-peak shear strength in our analysis. To obtain more human factor safety, the pen analysis were performed with plastic roller. The interface of the heat bleach liner or liner with geomembrane and geomembrane soil liner were modeled with interface elements using the shear strength envelope and calibrated with the peak shear strength. The pen analysis verified that the shear stress are equal in both interfaces. However, the relative shear stress has significant difference, as you can see in these graphs. The result demonstrates that the interface at the step are particularly more susceptible to reach the fault limit, but the peak shear strength is not mobilized. Additional failure mechanisms could be caused stress to overcome the peak shear stress, mobilized to the peak shear strength and causing a progressive failure. So the stability analysis using length were performed in some cases considering block failure along both interfaces. Peak and post-peak shear were considered in each interface. The interface has models continued elements. For these specific cases, the factor of safety obtained by PENS are close to the factor of safety obtained by them using the peak shear strength of the geomembrane with soil liner. Likewise, post-peak geomembrane soil liner scenario tend to be more conservative in the PEN because PEN consider both interface, behavior of the interface in the model, which estimate the shear strength mobilized along 2 interfaces. The analysis shows that the peak shear strength is not reached mobilizing. Thus, the use of the post-peak shear along the interface flat and steep zones could be over conservative. So, finally, as a conclusion, the geomembrane with soil liner interface shear strength increase based on the granular nature of the soil, and the sphericity height is a key issue to estimate shear strength values. The overliner with geomembrane interface shear strength increase based on the gravel content of the overliner, and in each path, both interface must be estimated based on laboratory tests. It's not advisable to assume that the weak interface will be above or below the geomembrane without performing laboratory tests. Alternatively, the stability could be evaluated with a composite failure envelope, which is defined based on the lowest shear strength of both interfaces, for the full branch of the normal stresses. These studies suggest some empirical relationship with preliminary estimate the peak and post-peak shear strength for overliner with geomembrane, and for the interface with geomembrane soil liner, we propose on the post-peak relationship. The analysis of the progressive failure is a good approach for designing heap leach paths. It allows to evaluate the shear strength mobilized along both interfaces. Peak shear strength for static conditions for platform will be used in stability analysis if numerical analysis show mobilized shear strength unless the peak shear strength, as long as having data and model higher confidence to support the analysis. That's all, friends. Thank you for your attention.
Thank you, Waldo, for this interesting presentation. We have time for a couple of questions. Do we have any? Oh, okay. Thank you very much. The next presentation, which is going to be in virtual mode, is titled CPT-based liquefaction potential assessment of leach for exhibiting microstructure. Expositor is Ronald Landa. He's a geotechnical engineer in Andes Asociados, SAC. Please join me to welcome Ronald.
Sorry, can you hear me? I cannot share my.
Yes. Somebody needs to tell me yes.
Do you want to tell him yes on the microphone, please, Arnaldo?
Yeah. Yes, we can hear very well.
And ask him to share his screen when he's ready.
Okay. No, it's not allowing me to share my screen.
Oh.
Nor my video.
Be able to make him the host.
Are we able to help him with it?
Yes.
Okay. We are going to wait for him.
There it is.
It should be good now.
Okay. In that we're ready. Or not, please.
Okay, thank you all. Thank you for that presentation.
And we're worried about it. Thank you.
Okay. Yes. So, thank you. My name is Ronald Landa. I am a geotechnical engineer at Andes in Peru. In my presentation today, I will share you, the screen tools we're proposing. We have adopted for liquefaction assessment of heap leach pads. And it's a large topic actually, and I'm going to focus on our proposal, how this can be used as a first screen tool to keep conservatism in a reliable range. These two are perhaps the most used charts in the last years as we have moved forward from the SPT world, the shear wave velocity and the CPT-based liquefaction triggering charts. They are reliable as we assess ideal soils, that is soils and has no microstructure. You have to recall that they were fitted to case histories just for clean sands. So on the charts on the screen, the CPT measures penetration resistance. So it's a large strength field test, while VS measures the soil shear stiffness, which represents the soil response at very small strengths. The cyclic liquefaction potential assessment is normally conducted under a cyclic stress approach, cyclic stress ratio, following the simplified procedure proposed by Sid and Idris almost 50 years ago. So while calculating the cyclic stress or the cyclic resistance ratio of leach ore, most of us have ended that while using BS and the CPT-based approaches, some differences are obtained in their respective estimates. In a heap leaching project, copper project in South America with high fines content, or geotechnical investigations were performed to assess leach pad slope stability. Of course, the SCPTU is the one preferred now. We have big 6 SCPTU soundings where, well, to assess this microstructure analysis. And well, they were conducted until a predetermined depth, because the predetermined depth was reached for avoiding damage to the geomembrane. So you'll see here the plots that are standard in a CPT chart analysis or CPT software, the cone resistance, the friction ratio, the pole pressures that are quite important for assessment. And of course, the Robertson classification charts. We must put some emphasis on the blue layers or the sky blue layers, which are the clay-like ones that are the most, that concern us the most as geotechnical engineers in heap leaching. The BS and BP measurements are shown here. And figure 1A depicts the estimated and measured BS profiles in grade. We have presented the estimates of BS as per the correlation proposed by Robertson, Felton and I, as a function of the CPT tip resistance. And in blue, the measurements themselves by the SCPTU geophones. So the mismatch is between this is evident, and it's already an index of the presence of microstructure in the ore for a QT-based estimation is consistent in clean sands, that is with no microstructure, right? And it's discordant with the BS measurements. So it can be also know this in figure 1B, where we depict the compressional wave measurements. And it's an interesting aspect in heap leaching as well. If the BP equal 1500 meters per second is taken as a standard, if we take that value from the tailings well, because it's really important for a definition of a steady state flow regime forming a defined water table. So this is not the case in a heap leach pad, which is designed ideally to percolate. The solution, of course, there's some issues with low permeability layers. And the fact that the VP less than 1500 meters per second confirms that the regime is a transient state one, characterized by isolated pressure heads, induced, of course, by these low permeability ore layers. That is the fines dominated layers that are randomly and heterogeneously distributed, which makes assessment very difficult. This is an output of the dynamic pore pressures. This is just one test, pore pressure dissipation test by the CPT. It's used for a definition of the transient pore pressure at the equilibrium. I said it transient because it's actually, it's not at equilibrium, because in a heap leaching, it's very dynamic and it changes all the time. So it's important because the pressure heads are practically transient all the way until irrigation is ceased. So, but they can be controlled under 4 thresholds as we calculated. Since we're not gonna avoid saturation. That's what some of the topics that they were talking yesterday. So saturation, it finds dominated layers within a heap, is what we need to control. So sometimes we use vibrating wire piezometers along the profile, so we can estimate more reliably this U0 profile. Well, this is the most important slide. That is the inclusion of a threshold cyclic shear strain on the standard cyclic stress approach that we all conduct in liquefaction potential assessments. The existence of a threshold cyclic shear strains supports the fact that there is a value where the pore pressure buildup is not possible. So we all need to recall it. Liquefaction triggering is fundamentally related to pore pressure buildup. and as you as you will see, to shear strains. So just to defend this point, Silver and Seat, 1971, Jout, Piquet, Stoltenkold, Dobridol, Chung et al., Whitman, Ladd et al., Hines, Su and Busetic, Cox, Chang et al., Hasselhoff and more, they all concluded that the threshold cyclic shear strain exists, which is approximately 10 to the minus 2 as a percentage, and is an aspect that links the onset of earthquake-induced pressure buildup. So it's it's uh, it's a backbone value or fact from the cyclic strain theory proposed by Dobry in 1982 that we can include in this standard approach. So on the other hand, Schneider and Most show that the lower limit of liquefaction resistance can be defined where the earthquake-induced cyclic shear strains are less than the threshold cyclic shear strain. So we need to review what's stated by Schneider and Moss in the paper of 2011, where they indicate or they define a way to define microstructure. This is the formulation equation 1. Well, here m is an empirical exponent, typically taken as 0.75. It's also supported by the investigation by Ricks and Stokey 991. And furthermore, the G0 can be equated by, well, as shown in this equation 2. So here's some charts that depicts the calculations made for kg for this 6 SCPT you have picked. And well, yes, we outlined the key aspects that induce an increase in the CSR. Microstructure, it goes with the soil, and well, there's an increase in the CR by cementation. Is not anymore an ideal soil. So there is cementation between particles forming microstructure along the ore at small strains. It's now an index of soil response at large strains. And well, it can be proposed in methodology that includes the calculations of this normalized read index to quantitatively assess the microstructure effects. So with these values, we can redefine the liquefaction triggering curve in the light, of course, of the threshold cyclic shear strain. To calculate the cyclic shear, the threshold cyclic shear strain is required to estimate it as shown in equation 3. The minimum value of liquefaction cyclic resistance represented by the cyclic threshold cyclic shear strain can be related to the CRR as presented of equation 4 and equation 5. So if you derive each line, then you'll end having this form of the liquefaction triggering curve, but equated. Now it's now empirical, it's now equated. So as reported in kg figures, where kg was almost ranging from 631 value to 900, we redefined the relationship of the CRR as a function of the threshold cyclic shear strain, and the kg, of course, as provided in the preceding equations. So the liquefaction triggering curve can be now modified as depicted in this line, in the shed lines, until reaching the standard liquefaction triggering curve. Here on the 1D nonlinear seismic response analysis, that is, it's required for simplified methods to calculate the PGA. Well, here the bold shed line represents the profile, the maximum profile, where it's factored by this famous value of 0.65. Well, the CSR max profile were obtained for a deepest CPT for 6 different time history series used for a 100-year return period event and 475-year return period to compare them at the end and show what are the benefits of including microstructure in the analysis. So these figures depict the calculated profiles of the maximum shear stress to the vertical effective stress ratio, obtained this 1D analysis. And well, it was conducted in terms of total stresses, considering that the soil seismic drain response is approximately equivalent to its undrained response before liquefaction triggering. And well, it's intended to fit the PGA in terms of the soil seismic response, the calculated soil seismic response. That is, it's each method that it uses or it is used in the light of the simplified approach. It's a package deal because we need to pick a PGA, a shear mass participation factor, and try to fit it to the seismic response I've made and obtained that way that maximum CSR. So here are the results for a 100-year return period event. The procedure proposed by Robertson has been considered to include the estimation of the CRR for clay-like salts, which are the fine laminated layers. It's delineation and heap leaching, where they are composed, of course, of fine-grained ore for a calculation of the equivalent CRR for the moment magnitude of 7.5. And this depicts the ore layers will not trigger flow liquefaction. For a QTNCS lower than 70, nor cyclic liquefaction, which can be expected between the 70 to the 120 in value. So this it's these layers are well, it's greater than those that would liquefy if the ore was a soil with no microstructure, because the curve shown in gray is the standard liquefaction triggering curve. So you can see that these results will indicate a leach ore with high Kg exhibit higher CRR at low levels of cyclic stresses, okay, related to 100-year return period, and that based on the QT-NCS relations. So under the proposed methodology, it's possible to avoid the conservatism of the simplified method while exploring the potential of the cyclic strain theory in its application to heap leaching. Here for the 475-year event, it shows that the microstructure is not sufficient to maintain mainly the ore cyclic strength. And in fact, almost the entire profile would trigger liquefaction occurrence with analysis assumptions using the simplified method. So these results indicate that the microstructure assessment is unnecessary since the leach ore will still behave as a sand-like soil or as a Holocene soil in which the microstructure is broken by the effect of the min equivalent cyclic loading, which is representative, of course, by the 475-year return period event characterized with a PGA of 0.50 Gs and, well, moment magnitude of 8.5. So what then? We need to check the vertical and the horizontal extension of fine laminated layers. That, of course, is a function of many parameters, yet the SCPTU density, that is the number of soundings that we need to make in a cross section, it's entirely dependent on this to define the horizontal extension. And well, it's also useful to avoid the over conservatism when we have no data and we need to to assume that everything's gonna go fine top to bottom.
Excuse me, Ronald, you have a couple of minutes, please, to
Yeah,
finish the
sorry.
presentation.
Yeah, I'm finalizing now.
We are almost done. Okay.
So the conclusion of this paper is that the heap leaching process, of course, may generate microstructure. It's possible to assess microstructure via CPTU, and the cyclic strain theory, based on the adoption of the cyclic shear strain of the threshold cyclic shear strain, can be coupled to the cyclic stress approach. And well, of course, one site-specific response analysis is required. And the fine-grained ore with high values of Kg, of course, for a low classification structure based on its consequences of failure, can exhibit a higher CRR at low cyclic loadings. So just finalize, I want to acknowledge Techniland for its fine translation work done for the paper originally written in Spanish, and of course, Andes for all the CPT data and the tools that made possible this work. Thank you all.
Very much for this nice and comprehensive presentation. Basically, we have a time just for one question. Oh, is the microphone? Oh, no? Do we have any question? No? Okay. So let's move to the next presentation.
Yeah. very good. So
The
thank you,
next
Ronald.
presentation title is First Radiographic Characterization of an Active Leaching Heap. Expositor is Tancredi Botto, CEO of UMO Mission, Cambridge, Massachusetts, United States. Dr. Botto is a senior applied physicist. He received his PhD in 1999 from the Vrije University in Amsterdam, the Netherlands, in fundamental electronuclear physics, and continued his academic research in MIT. Please join me in welcoming Tancredi.
Thank you very much for the kind introduction. My name is Tancredi Botto. I'm applied physicist, spent most of my career in computational research. What I want to present you today is the result of the first pilot of a novel biology. So the topic today is, the focus is really on so-called nuclear bulk density. Some of you may not be familiar with this name. However, you're certainly familiar with the conventional medical expert. It's essentially the same measure. Maybe more important, nuclear bulk density is the key characterization measurement in underground geophysics for oil and gas exploration. It's actually how you book reserves. The reason is because it's extremely robust and quantitative. So let me take a little bit of time to explain how it works. This applies to any type of nuclear bulk density measurement. You will have an incoming flux, incoming source, which I call I naught, will traverse a certain amount of material with a certain length. And you will be measuring the flux of this nuclear radiation that has traversed the material. The two are related by a very simple relationship. Essentially, this only depends on the bulk density of the material. You also see that there is a constant term. They argue that it's a fudge factor. It is not. It is actually exactly calculated. We use this framework, for instance, in delivering radiotherapy doses to patients, or in other, I think that's a good example to tell you how well we know this nuclear transport. Now, the measurement has other characteristics that is essentially is a counting measurement. You have to count quanta of radiation traversing the outer. And at that level is basically an absolute direct measurement of the density that you have. There is no normalization. You're not measuring ohms or volts, and you have to convert it. You're really measuring the number of atoms you have within a certain volume, and you're sampling that volume with microscopic precision. For the same reason, the measurement is also temperature and chemically independent, which is very important when it comes to geophysics. Now, when you're looking at nuclear bulk density measurement on the right, you have the conventional measurement system. In these cases, you're using either a radioactive source or an X-ray generator. Both are very expensive and both are very dangerous. But also both give you only a few inches of penetration surface. That's the standard versus gas. The alternative we would like to propose here is to use natural occurring background radiation, which in this case we call it cosmic ray, which is a bit of a misnomer. Because in this case, the source is not only available for free, but it's basically safe. So let me focus here on the picture, on the refractive picture on the left. Whether you like it or not, the Earth is bombarded by primary nuclear radiation from deep space. The moment this enters our atmosphere, it converts into a complex cascade of subatomic particles. There is a long-lived component of that reaches the Earth. And currently, all of us are being traversed by this particle flux, which we call nukes. Unfortunately, I didn't mention it. This is not entirely new idea, actually, it's not at all. Back in the 60s, there was the first scan of an ancient pyramid in Egypt was done using a mirror-radiography sensor. And obviously, it was good enough to make it a nice cartoon. Most recently, I'm bringing up two reasonably recent example of the 2D radiography done about 1 kilometer away of the volcano in Japan. You see that there's a density deficit in the center of the volcano. But a colleague of mine has done this work where she told a detector at 4 locations in a tunnel under Flattop Mesa, Arizona. And by having multiple observation points, now you instead of just bringing 2D radiography, now you can use 3D extraction. And in this case, you reconstruct densities in horizontal. You may argue if this is also good, why it's not so widely used? Well, the reason is because this is a passive measurement. And if you look at cosmic ray particles, cosmic ray meters, although this is extremely well known to a physicist, the fact remains that their number quickly decreases. So this table is for density of material with the density defined in the HV. So at surface, we all know there's 15 meter cosmic ray units per square meter. At 10 meters in a reaching you still have a million. But the moment you start going deeper, that number 50. And if the number disappears, that means that your measurement will take longer and longer. And your radiography measurement is essentially like taking a picture with a very long shutter time. We take a picture, a conventional picture, the shutter time is milliseconds. Here we have to wait days to weeks, depending on the depth of which we are. All right, so let's now focus on reaching operations, right? So the measurement would occur like this. You place a new imaging sensor under the asset, under the region. The region is the patient, and the sensor is the The sensor has to be able to not only just measure the presence of the arrival of the passage of the cosmic ray mirrors, but it also has to be able to determine its direction. And once you do that, you essentially measure the cosmic ray mirror flux at depth. And we have just argued that, this is essentially, you can transform this into a density map of the material, which is really glass PCC. Now, a density map, if you think of a dry heat or an initial stage, it's essentially the compaction map, because density in this case is not really the grain density, but it's the combination of density and porosity. But as but by the same token, if you look at this density map over time, and you look at now the volumetric equation, now you understand that if you have a change in density, you either have compacted it more, which is something that you can see from the outside, or you have added the material in the pore space of the heat, which is what we do every day. In this case, it's a liquid, which displaces air, that creates a density complex over time. And I can, knowing what the porosity is, I may assume it, I may need to measure it, I will be able to determine, knowing what the density is, I'll be able to determine the saturation. In other words, in absolute terms, you can express this in detail. So the whole story here is that, we need to conclude the nuclear bulk density is key for analyzing the productivity of the leaching heat, because it maps the fluid content within the heat. But it will also have significant application in understanding the slope stability of the leaching heat in general of any unconsolidated soil. All right, so the fun stuff. We field tested this spring in Chile, was a small leaching pad. You can see here part of the team on site. The sensor is in this HDPE pipe. I will talk about installation of the sensor. It's we are able to move it up and down this pipe with a very simple spooling mechanism. There is a data cable coming out. It's an optical fiber, so this can be several hundred meters, and the power cable that delivers power to the sensor. It's connected to a remote computer, which talks to a cellular net. All of this consume generally less than 10 watts, generating just a few megabytes of data. So the point I want to show you is that the measurement is statistical. Cosmic ray flux is low enough that you start seeing small variation, but it's stable. I mean, this is a physical fluctuation. 1/3 of the data points that are cycle once this is a good factor example. The mission, we want to distinguish between dry water and wet. Already by walking on it, you hear different sound, meaning the desert and densities. And also keep in mind that cosmic ray muons come from all angles, not exclusively. Ideally, I mean, in principle, even from 80 degrees from the vertical, but things get complicated. So we try to limit ourselves to analyzing only the first 75 degrees around the grid. This already gives a great cover. You're at 10 meters that the base of this cone is the diameter. All right, so we did some initial sanity checks. As the material was being deposited, we started moving the sensor to different locations. These different locations have amounts of materials, that is more information, and as you would expect, you would have less, you would detect less cosmic ray muons. We start from about 10 per second and we drop all the way. Then once we reached the final location, actually was the moment when the operator started the irrigation. And you see here a side view of the heap. You see the installation pipe. That's how the sensor is. And you see our Tancredi data function. So what is happening? You add in fluid to the pore space, and you immediately see that there is a change in the cosmic ray flux. And you will agree with me that this is statistically significant. This change is about 3%. And knowing the geometry of the system, we know that this means that there was being about 5% density change in the heat. What you expect? If you put in 20% more fluid saturation, you will feel about 50%. You can get better numbers, but it's absolutely quantitative. No much matter. And this all boils down to the volumetric equation. You will also notice that after this initial transit phase, there is a stationary state, which is what you expect. That's equilibrium state of the heat, and therefore this is the equilibrium fluid content. It just appears that there is a discrepancy, which we think is significant, but may need to be validated or investigated further. And this actually points to the fact that potentially at the end of the transit phase, you might have created from channeling some damage to the heat such that it doesn't retain fluid content that was designed. So what this means was this may mean that you wanted to operate with a fluid saturation of say 25%. Of the agglomeration phase. So 20% of the agglomeration, 25 to 30%, and you might actually be working with something which is a little bit less. Then the other thing is that we can generate the density. Now, to be perfectly honest, this needs to be normalized to what the incoming cosmic ray flux is. And we can take a textbook analysis, we can do an in situ measurement, we can do a good job or a less of a good job. And we also need to know the efficiency of detection. So our normalization factor at this moment is still a little bit uncertain, so I would like to call this uncertainty. But we can always generate the map which gives you the density variation in percentage. Because for that, we do not need to know any efficiency. The same if there is a cosmic ray flux variation, it's the same across the whole. So this is the other thing that I want to highlight is that this prototype sensor certainly has some issues, and one of them was that limited the speed. So when things are better, we're going to be able to expand the measurement. And we are waiting to be able to apply these improvements and then continue to scan as the operation progresses, because we will also working on a little bit of irregular. This actually is another important point. We see here density changes. It may seem they're a little bit large. I would agree. Part of the reason is that we don't have the perfect trapezoidal heat. And we have not accounted for differences in elevation, which we can. In fact, this is actually a representation of the heat scanned by a drone. So we have elevation points at each location in the heat. And therefore, the actual heat pipe is a question of incorporating this into our analysis, which is time consuming, but we don't expect it to be a showstopper. About the sensor installation, the hard part, well, we have to get under it. It's not a way. So if you have an on and off pad, we expect to have the utility every so many months. If you have a static heat, you can always install after you done your ripping on top of an existing level, and we're going to be able to image everything that we come on top. And of course, if we're talking about a greenfield, then it's a question of just digging a trench before you put the line. We can also install boreholes. Horizontal boreholes are always better. I mean, this is like throwing out a blanket to catch as many cosmic rays as you want. So surface area is really important. Horizontal boreholes give you the vast surface area protected to the vertical. Slanted boreholes are good at that. They can be cheap. This is obviously needed to get below the bottom depth of the static heat. But keep in mind that if we need to get to that point, we can also install the sensor several meters under the line. There is no need for us to be so close to the reach. This is a measurement, a penetrating measurement. Finally, if you have a very tall heat and really starts looking like a big pyramid, we can always install on the sides and on the side and also set someone. So we can always measure. And this is somewhat how this was done in reality, conventional HDPE pipe, which we join on site. We can learn how to do this fast, and we talk about it now. What are we going to do? What can you do with the data? We're getting asked this a lot. So the idea is that we're going to be able to display this data in some intuitive format. So the first deliverable is to make sure that if the operator confidence say everything here is according to your model, according to your plan. You see a green light everywhere. You go home and enjoy the video. And obviously, such an interface able to give you access to localized information on top of the heat with the actual food content, and so we will be able to determine, to what we think, what we have heard as the main pain point: too little fluid, too much fluid, and also get historical trends, because the measurement every couple of weeks we're going to have a new snapshot. If the measurement is continuous, we just need a couple of weeks initially to get statistics, then we can slide and visual. And also, let me highlight again, the data can also be projected in 3D. So however requires either multiple sensors or multiple position sensors. So other benefits, there could be many. Meaning, certainly, I've learned a lot in this conference. It's my first time here, and I appreciate the value of the model for the plug-related material. So very important to be able to stay on track. Our promise, our goal is to maximize method recovery by either scanning a whole each module and then continue to go back. And of course, minimize, optimize consumptions of oxygen. We heard today, sometimes you have less. Sometimes you have bags of fluid which adapt in the heat, so you won't necessarily be able to tell from the surface. All of this to give improved financial visibility, improved dynamic planning and operations, for instance, for ore removal, benchmarking the model, and then ultimately, you have this powerful X-ray imaging capability to recover, to correlate heat performance with other parameters, locations in the pit, performance of the agglomerator or weather. All right, so in summary, so geotechnical is not really something I invented. I built the first portal tool. We stand on the shoulder of the giant. It's a niche technique, but it's a mature technology. It's being applied in many areas, and it's a few areas actually you can be able to study more. The reason why it's not so widespread is that you have to be able to find the application where you have the right depth and the right. So in this sense, it's very well adapted to the monitor of the leaching heat or a tailing pond or a drilling source. As far as new vision, we are young to this business. It's our first pilot. We demonstrated we can operate remotely, safely, and no invasively. The operator we literally forgot about our system. We can map a vast area, and we have also shown that we can quantitative and accurately directly determine the content, not just a proxy of the actual dealing. And potentially they have already identified in China. So obviously, there's a lot of work ahead. Next would be to benchmark potential performance improvement with respect to the baseline. Those are difficult to get. And
I would like to thank you for your attention. I was answering the question. Thank you very much. Do you have any question for Chantley?
On this technology, would it be a feasible technology used for leak detection of liners on the beach banks?
Probably not, because you have the question is that where you can detect leaks under the liner, you have to be under the liner. So, I mean, probably not to the extent that you're not willing to drill a bore. If you're willing to go under the liner, yes, you could.
Yeah. We have different technology
Yes.
that use electrical resistance.
Yes.
It's a difficult technology to implement. And this, it sounds like, you don't have to do it on a daily basis. You go in and we have slotted pipes that have actually pipes that you put in underneath the pipe. Slide or sensors backwards and forwards. You could use it as a form of leak detection for that.
That wouldn't be able to detect any leaks under the liner. Huh? So,
What it would be, what it would be able to do is study rate concentration of solution.
I can talk more about it. Yes, please. Mike. All right, so maybe okay, don't even like that. Excellent point. So the first question is easy. I mean, you are a developer who like to build bigger systems. So because that means a bigger brand. I think with the current technology, we can this is currently the sensor is 20 centimeter in diameter, 18. We can easily double it. We can shrink it. Below 10 centimeters, we have to think a little bit harder, but still it's possible. However, there's always a performance state. We can make compensation longer, but you have to maintain enough surface area. So 15 million neurons per square meter per day, but you gotta have 1 square meter to see them, right? So it can be scaled. On the second question, you're absolutely right. We measure this and so yes, if you have a single projection, integrated along the trajectory, right? So you get an answer. However, if you imagine a multiple solution point and you convert it to slices, then of course you can see differences in densities, and I think that's what I showed before, pointing to that direction. So the length is something that you can measure.
Yeah.
Not quite sure what was your third question? Yeah, okay, yes. So we measure, you just have to think of the volumetric equation, right? So we measure the total density. We cannot distinguish matrix, grain, porosity. We have to measure it all. So now that's where you have an interpretation, right? So if you have a one constraint system and the density starts to increase, well, and you're adding fluid, then you will allow me to say that run directly. So you can do the same trick spatially. If you have uniform, you can always compare densities in this direction. So that gives you different ideas. So and that's how we can distinguish dry ore and wet ore. We have to do a time lapse, the benchmark. We have to measure the ore in the initial condition, and then we have to measure it afterwards for in different positions. So we don't directly measure water content, we measure density, and from the volumetric equation we interpret water. Likewise, we don't measure copper concentration, we measure blood density. But potentially you measure blood density to 0.01 grams per cc in a couple of weeks. Have other question? No? Okay, thank you very much. All right, the next presentation, style access technology, case study details, excellent results for hydrometallurgical precious metal and base metal recovery. Expositor is Nicol Nuku, Vice President, Mining Division, 6 Wave Innovation INC, Salt Lake City, Utah, United States. Nicol is a seasoned engineer with over 25 years of global experience in mineral processing, from laboratory test work to feasibility study, process plan design and engineering, construction commissioning, and operation with reference to base and precious metal, gold, copper, molybdenum, and silver, and other products, including rare earth, oil sands, diphosphate, monophosphate, beneficiation, where mineral processing techniques are very important. Please join me to welcome Nicol.
Good afternoon, fellow guys. I'm glad to be here to make this presentation. Today I'll be talking about some of the interesting aspects that we have achieved with the ESOS technology. ESOS technology is just based on a molecularly imprinted polymer, which actually has been used in the recovery of mainly gold and silver. So with this particular presentation, this was work that was done in Chile for the recovery of gold, and that is specifically selectively recover gold and silver from ore or leach solution that is highly concentrated with copper and the presence of sodium chloride. Before I continue, I just want to acknowledge the president, Dr. John Blackman, and also the executive vice president for Chief Development Officer, Mr. Sherman McGill, and my colleagues at 6 Wave Innovations. So this is the itinerary, or this is the content of this presentation. I'll walk through the laboratory test work that we did first, mainly to figure out that this is a good or adsorption unit for the recovery of gold and silver from leach solution containing copper as well. Then I'll progress to what we did on the field, and then I'll look at some of the costs attributes related to the ESOP speeds, and then I'll focus on some of the potential enhancements that this provided environmentally, social, and governance. And then I'll discuss a little bit of the results and then conclude. So just like we all know, the trend right now is to look at a technology that will provide improved recovery and also allow for cost reduction in operation, and will also benefit the environment in the form of ESG ratings. With what we did, the work we did, and what we did at the field, we realized that if the client was to pursue the ESOP speeds, he was going to end up with a reduction of 703 tons carbon dioxide per year, which is definitely a good thing for ESG boost. And in addition, operational cost savings of $0.4 million per year without thermal regeneration. And also operational cost savings due to reduced fuel usage of about $0.05 million per year. And we reckon a total of $0.22 million savings because you won't be generating fine carbon. And overall, annually, we reckon estimated savings of $0.45 million per year, and or $0.093 per ton of ore treated for the 7.2 million ton the company was planning to treat. And all this information was actually resolved together with an independent client, SME, that we work with. So to go ahead, I'll just go with what we did in the lab. We did a simple bottle roll test and I did a single pass of solution for 24 hours. A few of the parameters that we had to play with is as follows. The ore grade we handled was 0.44 grams gold per ton. And because the client was going to be using water that had been treated using reverse osmosis, client recommended we had sodium chloride of about 207 ppm in the solution. And that was what we used for the leach, the bottle roll leach. Now, when we ran when we leached the solution, we collected enough solution to run 2 adsorption tests. In fact, 4 adsorption tests, 2 for the isox beads, and then 2 for the activated carbon. With the isox beads, we ended up with improved recoveries for the gold, or selective recovery for the gold compared to the copper, but still we picked some copper. With activated carbon, there wasn't very good recovery, and there was virtually no copper recovered. Results show that with the single pass, we're pulling about 70% of the gold and 37.3% of 37.3% respectively. Gold, 70 and then 37% respectively for the isox and then activated carbon for gold, and then 25 and 3% for the copper. Now with that, what we did was we did some extrapolation using a number of tanks, and we realized that if we put in 5 tanks, we're going to have close to about 99% or 99.75% recovery compared to 90% recovery for gold alone, as compared to activated carbon, which will be 90%. Now, with that in mind, we realized that, well, that would be a good thing to run on the field. We reached out to the client, and client was actually excited about this and wanted us to come to the field to run this test work. The same thing was the result we had for copper when we did the extrapolation. We're thinking of recovering 76% of the copper compared to 15% using activated carbon. Now, with that in mind, we realized that if we recover the gold, we can also recover the copper, and depending on how our strip performance, we would be cleaning the beads and making it available to recover more gold and more copper as well. So on the field, we had 12 tanks of heap columns set up to recover close to about 60 liters per day. Now with the field test, we ran 145 hours and we recovered 693 liters of PLS, and we used 90 mils per minute of flow through the adsorption columns. The adsorption columns, we had 90 mils of isox beads set up in the columns. Throughout the 145 hours that we ran, we did see a trend where the gold in solution was actually reducing throughout the period that we ran this test. We also noticed that the silver was virtually not really being absorbed, and then the copper value was also rather increasing in the leach solution. So what was happening was that all the gold first leached out, followed by the silver, and then the copper. So towards the end, we had more copper in the solution, and then we had less gold in the solution. In other words, if we had that circuit in place, what will happen is we'll be in a position to recover all the gold and then all the silver, and then followed by all the copper. This is the cumulative metal absorption that we trended over the period that we were on site. Now, with that information, we did try to see what was actually happening at each point across the absorption circuit, in particular with reference to column 1 through to column 6. And using statistical method, we derived a curve to see the recovery of the different metals that we had for each hour that we had the plant running. In this particular case, we looked at the first 12 hours to see how the absorption kinetics was behaving. And it looked very good because the gold was actually showing low, the gold was actually showing very low concentration in the last tank 6, which kind of buttressed what we found in the lab. The copper, on the other hand, was virtually not being removed from the circuit, which again buttressed what we had in the lab. And the silver was also being pulled out of circuit, which buttressed what we had in the lab. And we ran the last 8 hours. We had similar scenario that we had for the first 12 hours. But in this case, the copper was already high in the feed solution, but yet still, we had very little copper getting absorbed on the beads, which was very good indication. And to a large extent, this did not affect our gold absorption on the beads, which also showed excellent recoveries even in the last tank 6. Same applied with the silver. With the strip, one of the good things that we realized, well, this was a setup we put together for the strip, both the sites and then the schematic design. It was more like a continuous strip circuit. This was done under ambient pressure and ambient temperature. There was virtually no pressure buildup in here. And it worked perfectly as compared to what we are known to use for carbon when we use the AAR circuit or the Saavedra circuit. This is some of the strip results that we had. Very impressive strip times. We're stripping all the gold in less than 3 hours. And at atmospheric pressure, 60 degrees C, and strip solution used was 1 molar urea and 0.5 molar sulfuric acid. Cost-wise, we did not do any regeneration. And so we wanted to see how it will look like if we compared the thermal regeneration with thermal regeneration of carbon with the isox, where we did not do any thermal regeneration. And this showed a lot of cost savings. In other words, we're showing close to about 422,000 kilowatt hours per month saving if we should go with isox. Now, what the client planned using for activated carbon was the vertical main fan carbon regeneration circuit. Now, with the vertical main fan carbon regeneration circuit, client recall that he will be using 308. He'll be using 4.3 tons of carbon per ton. In total, 34.5 tons of carbon in the circuit. Now, with that at the back of our mind, we realized that the vertical main furnace that will be used will be the 470 the one that draws 470 kilowatts, and that would result in 406, that would result in 4,000, that would result in 4,603,680 kilowatt hour per year. Now we intended to just use what the client will use in case he just decided to use the 308 kilowatts for his second, or you intend to use 2,664,019 kilowatts hour per year. With that, what we ended up with is a scenario where client will have a cost saving of about $0.056 per ton and $0.4 million per year and $0.05 million per year, given that we'll be using just about 50% of the combustible fuel that will be used in case he decided to go with activated carbon. Overall cost savings was about $0.063 per ton of ore treated, or a total of $0.45 million per year. In total, clients would achieve a total of $0.093 per ton of year. So potentially, looking at all those figures, given that he'll be treating 7.2 million tons per year, he will require an average of 69,712 liters per annum for maintaining heat energy combustion. Using ISOX, it is anticipated that only 50% of fuel will be required to keep the strip at 60 degrees C, since there is no need for stripping 8 hours, as is the case with loaded activated carbon. Subsequently, the amount of fuel saved will be about 34,856 liters per year, which is half of what would have been used had he gone for activated carbon. With 2,739 grams carbon dioxide generated per liter of diesel used, the reduced emission resulting from stripping the exhaust beads is on the order of 91.99 tons reduction per year. Similarly, with thermal regeneration of activated carbon, the client consultant determined the fuel reduction is 266,402 liters per year. This reduction equating to carbon dioxide emission is estimated to be 795 tons per year, as per also calculated in figure 11. The total reduction in carbon dioxide emission for using exhaust compared to activated carbon is 795 tons per year, as mentioned. So in brief, and with discussion, we realized that the predicted 99.75% cumulative gold recovered using exhaust beads for a 5-column adsorption circuit suggested that a 6-column adsorption circuit was optimum for field tests in combination with the strip. And removal of copper from solution using a predicting model suggests 4 times higher for exhaust compared to activated carbon. However, it's well known from lab work that gold is preferentially adsorbed to copper in succeeding adsorption columns in a circuit. It should be noted that the laboratory test was data derived from a 24-hour single pass, and therefore the field test was warranted to investigate and ascertain the adsorption kinetics over a longer period at more operationally relevant conditions. And that is what we did on the field. And furthermore, the field test results also found that per the model, derivatives in figure 7 show 98.61% gold recovered, 88.6% silver, and 22.46% copper adsorption efficiencies, respectively, within the first 12 hours of the bench scale adsorption. Similar results showed for the last 8 hours. And this information actually suggested the good performance of the exhaust bead, which is of one of a unique characteristics of the beads itself. So in conclusion, the use of exhaust technology at heap leach mines can result in improved gold absorption compared to activated carbon, lower gold and /silver in tailings, no losses to carbon fines, reduced carbon dioxide emission or carbon footprint worth approximately 0.93 million annually in tradable carbon credits for the 7.2 million tons of ore that was treated. This is a potential enhancement of environmental, social, and governance. We also realize that there will definitely be a reduced energy consumption, resulting in US dollar 0.45 million per annum of savings. Thank you. Hello?
Is there any question for Nicol? Yes, we have two. Okay. Could you please use the microphone? Thanks.
Technical time for implementation. So the question I have is in terms of the particle size of the beads, I know for carbon we use X6 by 12. So what particle size do you guys have? And also how is the attrition rates compared to the carbon?
Okay, so the beads we use in 8 millimeters is between 8 and 1.2 millimeters. But there are some other good aspects of these beads. These beads is actually lighter than carbon. And with that in mind, the way we actually recommend a particular design for the absorption unit, which we have designed in-house. And in fact, it's also being used already in the racing industry. And that was actually a design similar to what I would say, it's a design that uses a restraining method of the beads in a tank and allows the solution to flow out of the tank. And you can push as much flow rate that you want without having the beads leave the tank, the absorption tanks.
Thank you. The next question is John, thank you. Okay, sure, for sure. Take our time.
So because where we do have a lot of mercury in the water, we just have mercury going to the carbon. So with your being mercury and you have mercury.
I can't hear you.
So what I'm asking is with the mercury that we have in the water, so if you have activated carbon, you do have some mercury going on activated carbon, then it goes to the strip that you have to do with mixing. So with your bead, you have mercury going on that bead, and yes, how do you deal with that during the strip process?
Yes, the beads are actually very good at recovering mercury. So if you have mercury in your ore and it is leached, the beads will recover it, and it strips very well the same as gold. And you can recycle the beads back into circuits and use it for absorption without, as if there was nothing on it. The beads are very spongy, and they don't end up becoming brittle like what you end up with when you have a mercury loaded on activated carbon.
Yeah, there is one more question for you, Nicol.
Nice presentation, Nicol. My question is, what is the life span of your exhaust technology versus the carbon, the activated carbon?
So with our beads, they don't wear. In fact, the configuration of the nature of these beads is spherical, and they don't wear. And they can stay for, we have run a few tests that we are yet to publish a couple of papers on, and they can stay in for a very long time. You can treat it, it will not wear. And and because of, as compared to carbon will wear. So what we have, the way we've handled the beads now, we handle them more like a capital item. In other words, you could buy them as a capital item and have the guarantee that they will actually stay for a very long time, with very minimal wear, but definitely everything has a lifetime. So this will eventually wear out. But we think it has a lifetime of about 4 years plus before it actually wear off completely.
Okay, thank you very much, Nicol.
Thank you.
The next presentation is titled The POE Nicol Privilege Commercial Plant. The expositor is Omar Caceres, Project Implementation GM, Brazilian Nicol PLC. Omar is a metallurgical engineer for the Universidad Industrial de Santander in Colombia. He has over 20 years of experience in mining. We are focused in nickel privileging. He worked for 14 years in Colombia on process engineering, information management, business improvement, business and production planning, corporate reporting, cost control, and investment evaluation. Please join me. Welcome.
Good morning. I'm here on behalf of Brazilian Nickel to give you an update on the status of the POE Nickel project development. So I'm going to touch base a little bit on the history behind the POE Nickel project, the strategy to develop this project, and the current status of our small scale operation. So Brazilian Nickel was set under the assumption that we will become nickel producers using heap leach as the extractive technology. The technical group behind has an average of probably 10, 15 years experience working on the technology development based on copper experience and other heap leach operations experience, all the way from bench scale tests to demonstration use. We probably built 2 or 3 pilot plants, demonstration facilities, working for big companies, but those projects, for reasons that doesn't matter now, they never saw the light. So POE, the POE deposit was the result of a screening, very comprehensive screening process of over 100 deposits, knowing what we wanted to do, which was use heap leach as extractive technology. So kind of an ideal deposit, if you consider all the aspects, location, infrastructure, the actual amenability for leaching. So kind of a perfect start for us to break ground and do the first nickel, the greenfield nickel operation. To develop the POE nickel, I mean, we started this back in 2015. Not really a great time to attract investors. So we come with a split strategy. We did all the demonstration, proof of concept, validation of our design criteria. And after that, we just said, well, for us to really break all the preconceptions about application of nickel heap leach for laterites, we'll have to put out an operation. So the idea was to retrofit the demonstration facility and come up with a continuous operation that we call PM2000. In parallel, we carry on with the bankable feasibility study for a full scale, and the table just showed a comparison of the scale. But for us, the PM2000 is the ultimate strategy to bring people to site, show them the overall process running. It's the exact same flow sheet, different ore, yes. We obviously, being a junior mine, we use the best nickel that we have in the deposit, so we can make some money out of this small scale operation. Yeah, but everything else is really the same. So this is the flow sheet that we're using. Open pit mining, pretty straightforward. We don't have to do any sort of selective mining based on mineralogy. We just have a very specific target on chemistry. Crushing, two-stage crushing, open circuit, also nothing fancy. Agglomeration, we use sulfuric acid for two reasons. Conglomerate the fines, but especially to kick off the extraction process. Stacking, also nothing fancy there. Overline conveyors, grasshoppers, radial stacker. Dynamic leach pad. POE is also a really, I already said, it's a really good location. Plenty of real estate for us to do a leach pad that we need for the full scale and to grow if we have the resources to grow. Drippers, low irrigation rate, and not because permeability issues, but because we want to maximize the acid use. Then the downstream process, that's where a little bit of innovation we have. We use ion exchange as the purification system, so we can achieve a really high concentration NHP. We're targeting 37 to 52% nickel, and we already produce that in the small scale. Also, the ion exchange allow us to have a byproduct with cobalt, and we're going to produce 3 residues: the spent ore, the impurity removal, which is mostly iron precipitate, and the bleed, which is basically magnesium cake, used to keep the magnesium level in control for hydraulics. All of them filtered, so no tailings, and commingled disposal in a line facility. Couple of pictures. On the right side, the demonstration plant, very small leach pad, 20,000 tons, only 2 cubic meters an hour. That was the capacity. So we retrofit all of that, build a new leach pad, 120,000 tons capacity. We split that in modules. Every module is 12,000 tons, 4.5 meters high. That's been our, after series of column work, that's been the height that we select. And it was the same height that we tested in the demonstration plant. So no changes there. Downstream plant, because now we process in 22 cubic meters an hour. So we have to build a bigger impurity removal system. The ion exchange unit allow us to use all equipment from the demo plant to do the NHP precipitation and the ore precipitation. So we built the PM2000 project. The construction was last year. We finished in the first quarter this year. Start mining, stacking in March, April, irrigation in May, first product produced in June. Right now, we have 7 modules in operation. The downstream plant is running at 90% capacity in terms of nickel throughput. Nice thing about this project, absolutely all the operators are local. So although it's very nice, it's very challenging because there is no mining history in this region. So we have to educate all of them, but we're doing it. And in parallel, as I mentioned, we completed the bankable feasibility study. We have all the environmental permits, and we are presenting the project, the full-scale project, to the investment community to get the financing, get the money, and start building it. A picture of the current pit. As I said, nothing really fancy about the mining, pretty straightforward. We know blasting for this particular area. So far, excellent reconciliation between the plan and the actual results, the actual order we get. Leaching performance, also pretty amazing. Alex touched base yesterday in his medicine presentation. Pretty amazing. Obviously, we know this is going to change. Here in this corner, we've seen the individual modules to see how the operators start playing a role. So we have one module that was behind in terms of the target acid addition with the agglomeration. That's going to have a consequence in the leaching performance. The main reason why this is so good is because everything matches the model, the actual operation, the actual ore chemistry, and everything else match the model. So it's a good validation. Now the latest models, they start changing. So we start seeing different magnesium to nickel ratios that will have a consequence, and we will see curves that will from the current model will go apart. I'm not presenting it here because they just have the 60 days, so it's not really very conclusive right now. Another great chart is this is presenting the kilograms of magnesium versus the kilogram of nickel extracted. Really great correlation. And since our approach to heap leach is all based on acid availability, this is how we control it. So if we can guarantee that we maintain control of this ratio in terms of extraction, we know that we're going to achieve the ultimate extraction that we carry. In terms of processing plan, we thought about presenting some numbers, but really it's a lot of noise in the data, especially because the education process of the operators. Overall, we're achieving the target nickel recoveries in the different stages of the downstream plant, but it's just the continuity of the process that is being affected by that education process. This is just a picture that I like to show about the ion exchange application. This is the feed. Right now it's pretty good. It's 12, 14 grams per liter nickel in the PLS. We expect that to go down as the heat matures to maybe 6 or 7. And what the ion exchange does is act as a concentrator. So the LWA, which is the darker green, has 40, 45 grams per liter. So we have a much smaller volume to treat and a much more pure solution that then we turn into a nice green NHP with 47 to 50% nickel right now. So this is an actual picture of the very first nickel that we produced back in June. Very exciting moment. And we are in the process to complete the first shipment this month. So that's pretty much it in terms of the update. As I said, we're ready to start building the big plan. Obviously, we need to close the deal with the investors. Ultimate goals, as we already reporting on ESG. We have already investors that are very sensitive towards that. So we already fully engaged on that. And yeah, looking forward for a very exciting implementation of this project.
Well, we have time for questions. Mark?
I had a great presentation. Thank you. I guess I missed the presentation. Like the historically leaching laterites has been kind of taboo. I'm just curious to see what would you say separates your process away from other operations, and how have you been able to overcome the limitations around permeability with laterite ore?
Yeah, I mean, as I mentioned at the beginning, Brazilian nickel was set by all a big group of people that we all work in the heap leach development for nickel laterites. We all got frustrated because none of our projects saw the light. So one of them was had the courage to put this company with the target of using the technology. So we believe on the technology. We have plenty of demonstration, a lot of data to support that. We know what worked, we know what wouldn't work. Yeah. So in terms of the permeability, it's very site specific. This is a mostly saprolitic deposit. So silica content of 40%, so it's perfect. No clay, no significant clay, no limolitic. The limolitic portion is probably 10%, so it's fantastic. Yeah.
Thank you, Omar. That's very, very nice. Could you comment on sulfuric acid consumption? And then there must be maybe a lime or limestone consumption.
Yeah. Well, on the acid consumption, we also take a slightly different approach than everyone else. Nickel, one of the preconceptions of nickel is that it's a high acid consumer, and in fact it is. Yeah. So the acid plant or the acid supply becomes your constraint. So we work the other way around. We define what is the acid supply capacity that we can do, and then we match everything else backwards. So in terms of, instead of us defining a fixed target extraction, we said with the amount of acid that we have, what is the extraction that we can get? And we do the mine planning accordingly, targeting obviously the heights. Yeah. And sorry, and the second part of the question, another perfect situation of PLB, 30 kilometers away, huge, massive limestone deposit. And yes, you may be advised.
Sorry, no question. Did you do a trade-off between ion exchange and solvent extraction? You talk about why you ended up with ion exchange.
I personally didn't. Other person in the group did it. I'm not really familiar with the details. I'm sorry. I know that there's issues, significant issues in terms of efficiency, current, impurities that will affect the solvent extraction performance.
So
help us. I was more on the ion exchange side. I did more than 2 years of piloting, continuous piloting in Colombia, and the results are just fantastic. Sorry, I can't provide more information.
The motor stand.
Hello, Omar, that was a good presentation. Just a few things on the heap leach. My understanding is that it's an on-off pad, and I don't know what your actual maximum height is on the pad. But you'll fix your dry filter cake from the residue and back into the reeds. What is your agglomeration process if you're going to have one on this pad? Is it just a belted agglomeration for the hole?
We do drum agglomeration.
Okay.
Yeah, and we add some concentrated sulfuric acid. And it's not so much for permeability purposes. Obviously, there are benefits, but it's mostly to keep and have a very high extraction. I'm talking 15 to 20% in the first week. Yeah, that's the main reason why we do agglomeration. And as far as height goes, there is a trade-off, and the height that we pick is after a lot of test work at different heights. Basically, the higher you go, if permeability allows, the leach cycle becomes longer and longer and longer. So it's a trade-off, and we end picking up the 4.5 meters as the optimum in terms of acid consumption, leach cycle, and ultimate extraction.
Yeah, and then my next question was, why did your solution concentrations decrease for ongoing operations. It's probably due to not taking off the first lift, it ended up being on off pad and on different heights in the pad.
I mean, it drops. How can I say this? It is the nickel. What we've found over the years of test work, we can split the different nickel extraction into 3 stages. One is the portion that reacts to the acid that we add in the agglomeration. Then the next portion is what we call the readily available nickel that is easily accessible by the acid. And the last bit of the extraction is the most difficult one. That's why we use low application rate to allow that contact time. And obviously, the nickel grade reduces as we exhaust the ore. Yeah. Right now, because we are in the ramping period, we are adding more and more ore all the time, pressure ore. We are keeping this high grade in the PLS, but we know that once the path is full and you have all heaps almost at the end of the curve and new heaps, it will balance down to what I mentioned before, 7. Thank you.
Thank you very much. Well, with this presentation, we have finished our session today. On behalf of the organization or organizers of the Privilege Pack Solution 2022, I want to thank you, the sponsors and exhibitors, for their support. Also, I want to thank you, the whole colleagues, with their present and also the active participation have helped for the success of this event. So I invite you to go for lunch in the room 91. Thank you very much.